Hello, everybody. Thank you for your thank you for your invitation. It is a pleasure for me to be among you in this scientific event. The title of my presentation is Annealing Temperature Effect in Structural and Photoluminescence Properties of Yttrium orthophosphide doped by cerium trivalent nanophosphates. Firstly, I introduced myself. I am Dr. KAOUADJI Badis. I am from Algeria. I have a PhD physics, materials science, teacher research at Abdurrahman University of Bijaya. I work on nanomaterials based on rare earth orthophosphates in collaboration with two laboratories, Laser Department Nuclear Research Center of Algeria with Dr. Lakhdar Gerbouz, and Laser Department and Vinsha Institute of Nuclear Science with Professor Miroslav Dramakanin and Dr. Dragan. My skills and expertise: nanomaterials, luminescent materials, photoluminescence spectroscopy, solid synthesizer, phosphorus, inorganic scintillators. Recently, scintillators based on inorganic materials doped with trivalent lanthanide agent have received great attention from the scientific community. Modern technology requires characteristics of scintillators that are more efficient than those provided by traditional ones, particularly in terms of quantum efficient, time response, mechanical stability, and resistance to radiation. In recent years, particular interest has been focused on very specific group of scintillators materials based on phosphides, which are the scintillator based on orthophosphides of lanthanide and doped with rare earth iron. Now, in this work, we studied the effect of annealing temperature on structural and photoluminescence properties of cerium 3-valent doped yttrium orthophosphide nanophosphate. Now, why yttrium orthophosphide house is a promising candidate for inorganic scintillators. Yttrium orthophosphide matrix has excellent chemical and physical stability. In this table, I summarized some interesting properties of the yttrium orthophosphide matrix. Cerium doped yttrium orthophosphide nanopowder were prepared by Solgel method. Samples were annealed at various temperatures. The different steps of powder preparation by using Solgel process are shown in this slide. This figure shows TGA and TDA curves of yttrium orthophosphide xerogel. According to this figure, total mass losses of about 18% was observed after the TGA analysis. First mass losses of about 15 is observed around 150 degrees. This loss can be attributed to the removal of adsorbed species such as water molecule. A second mass loss of about 65% is observed at or higher temperature at 250, which can be attributed to disappearance of the residues of synthetic organic solvents such as ethylene glycol molecule. From this temperature, the crystalline growth current and no significant mass losses is observed. These mass losses are accompanied by two relative intense peaks of differential thermal analysis. This figure shows the X-ray diffraction patterns of yttrium doped by cerium ion powder annealed at various temperatures. All the diffraction peaks observed on the X-ray diffraction pattern are characteristic of the tetragonal phase. The obtained results have advantages in comparison to previous work for similar system. In other work, the tetragonal phases for temperature below 400 is not obtained. It is indeed that our results is very interesting because we obtained the tetragonal phase below 400 degrees Celsius. The average crystalline size increases with inhalation temperature from around 5 nanometer up to 30 nanometer for the sample annealed at 300 and sample annealed at 1050 degrees Celsius, respectively. Also, in the same time as given, the volume cell decreases with temperature. The decreases in volume cell and the increases in crystalline size are related to improvement of the crystallinity and the decrease of the density of defects. This figure shows scanning electron microscopy of yttrium orthophosphate nanopowder annealed at various temperatures. The SEM images of sample show that obtained powder consists large quasi-spherical particles with varying sizes, ranging from a few nanometers to several hundred nanometers. The bigger particles are composed of 10 of smaller particles with the average diameter of 30 nanometers. This powder have an agglomeration particle due to effects of annealing temperature. The influence of annealing temperature on the photoluminescence parameters of yttrium orthophosphate powder was also studied. In this study, it was presented the emission and excitation spectra of the powder. This figure shows the excitation spectra of yttrium orthophosphate doped by cerium trivalent nano powder. The excitation spectra of the excitation spectra from all annealing temperatures shows similar spectral feature with the same position of absorbing band. Under all the observed excitation or absorption band, it attributed to interconfigurational transition of cerium 3+. Now, according in this figure presents the emission spectra of yttrium orthophosphate nano powder. According to this figure, the characteristic emission band of cerium in yttrium orthophosphate matrix with corresponding transition were observed only in the powder annealed at the emission band of cerium in yttrium orthophosphate were observed only in powder annealed at 900 degrees Celsius and 1050 degrees Celsius. The absence of photoluminescence emission in this powder means that there is no substitution of cerium 3+ in yttrium 3+ state. It could be explained by segregation of the doping ion in the obtained phase and to oxidation of trivalent cerium to the trivalent state and under lower annealing temperature. In addition, at lower annealing temperature, the smaller particle will obtain. Hence, the reduction of particle size obviously affected the local environment of cerium 3+ in yttrium house, probably due to change in large surface to volume ratio and amount of defect on particles surface. For conclusion, in the present work, we have presented the effect of annealing temperature on the structural and optical properties of nanomaterials of the yttrium orthophosphate doped by cerium 3+ ion nanopowder were synthesized by an experimental protocol based on the social method under the same conditions and annealing at different temperatures. The analysis indicates that all powder have crystallized in pure tetragonal phases. The average crystallite size increases with the annealing temperature from around 5 to 30 nanometers. The characteristic emission band of cerium 3+ in the yttrium orthophosphate matrix were observed only in the powders annealed at 900 degrees and 1050 degrees Celsius, while other powders obtained at lower annealing temperatures have no photoluminescence emission bands. This phenomenon can be explained due to the either segregation of doping ions in the obtained phase and to oxidation of cerium trivalent ion to the cerium tetravalent ion, or due to the change in the large surface to volume ratio and to amount of defect on particles surface. Thank you for your attention.